This is special lectures about Lagrangian physics, and the topic is what is the theoretical particle physics, as is some overview. First of all, we know that all the ordinary materials that consist of the atoms, as known as the periodic table in chemistry. But atoms is divisible the particle. There are some nucleus in scientists and electrons with the orbital. And such as the electron distribution can be calculated by the quantum mechanical orbital. And the nucleus is also divisible with some several nucleons, such as the proton and the neutron. And the protons and the neutrons are also divisible. For example, protons are consisted with the two up quarks and the one down quark, and the neutrons case that is the one step quarks and the two down quarks. And in current levels, the such electrons and the quarks are indivisible. There are almost point particles in the experiments of the elastic scattering. And we say that the such electrons and the quarks, such elementary particles are the most fundamental elements in the particle physics thing. And such as some electrons that are generalized to the some more elementary particles. There are some elementary particles in the standard model. First of all, we already there are some up-quark and down-quark which consists of proton and neutrons. And there are some another quarks with some more heavier masses, and they are shares the same properties or quantum numbers of the up and down types the quarks. So it called the generations with each masses. For example, in the up-type cake, there will be the up cakes, down cakes, and top cakes as the generation 1, 2, 3, respectively. Similarly, in the down-type cakes, there will be some down cakes, trench cakes, and bottom cakes with the generations 1, 2, 3, respectively. Such a same quantum numbers mean that it has the same electric charge and the weak charge and isospin thing. And such a character has a color fiber, so it consists of the hadrons by the strong interactions. But in the lepton case, it doesn't have the colors fiber, so they do not interact via the strong interactions, so they didn't make some of the composite particle. And the electrons is well-known examples of the lepton, especially the charged lepton, which has electric charge minus E. And also there will be some generations with the mass during electrons, muon towers. And there are also neutral leptons, which doesn't have the electric charge, so it doesn't interact via the electromagnetism interactions, but they has a certain neutrino has some weak charge, so it is only interacted via the weak interaction, so it's very hard to detect. So there is an electron neutrino, muon neutrino, and tau neutrino. Such a crystal leptons that are the elementary particles which consist of the matter, and it's partially the crystalline leptons that has a spin 1/2, so it is called the baromeans, which is the spin is a half integer. And there are also some integer spins, elementary particles, so-called gauge boson and scalar boson. As an example of the gauge bosons, as a spin 1, there are some proton, W jet boson, and gluons. The proton series some mediators particles for the electromagnetism interactions. If there are some electric charge for the elementary particle, then the interactions with the mediating proton. And similarly, if there are some of the weak charge for elementary particle, they interact by the mediating W jet boson. And if there are some of the color charts, and there will be some interactions via the mediating gluons. So such as some of the gauge bosons, there are interactions particles that are both carriers. And there are also spin-induced scalar boson, which is called the Higgs, and the interactions with the Higgs gives that some of the mass of the fermions and the gauge bosons by the back mix of Gaussian polarizer of the Higgs field. So the point is that there are some elementary particles calculated in the leptons, and they have a specific charge, like the color charge, big charge, and then some electric charge, such thing. And there will be some of the interactions between these such as elementary particles will be other both carriers such as gauge boson and scalar bosons. So in one sentence, there is elementary particle and their interactions via the some of the gauge boson and scalar boson things. And we can describe sort of such interactions as a Lagrangian form that keeping about some of the fundamental systems. There are some several terms in the standard model Lagrangians. In the first line, there is up mu nu and up mu, which is field strength. That is some of the kinetic terms of the spin one gauge boson. And in the second line, there's a psi, d and psi. Psi is some spin one half fermions, like some cakes and lepton. And d is a covariant derivative, which is defined by the partial mu minus some coupling constant times the charge times the gauge boson. So such covariant derivatives provide the some gauge interactions between the spin one bosons and spin one half fermions. And in the other lines, the mu pi also it provides the interaction between the gauge boson and the scalar boson. And in the potentials V pi, it includes the mass of the pi scalar boson and the sharp interactions of the scalar boson thing. And the final lines called the core interaction is the interactions between the spin half fermions and the spin Jews scalar boson. And the several possible interaction vertex of standard models are represented in the right-hand side as the bigger representations of the Feynman diagrams. In the first line, there are some strong interactions. Q is the representation of the Kirk's energy is gluons. So there is some interaction between the Kirk and the gluon vertex because the Kirk has SS3 color charge. And also because of non-abeliance property, there are the self interactions of the gluons is possible through the three of vertex. And all leptons and the cakes has electric, no, not electric, weak charge. So there will be some interactions with the jet and double boson. For example, jet boson, there's no change of the kinds of the particle. There's only energy changes. And the double boson case, there are some changes of the kinds of the particle. For example, neutrinos become electrons and vice versa. So the D-type circuit becomes U-type circuit because double boson has electric charge, double minus plus. And there will be some of the mixings of the generations from the some lepton mixings, like Kirby mixing things. And there's some electromagnetic vectors positive for the electric charge is a particle like the charge left in the Kirk. And there's a non-abelian property, there will be the self interaction with the that's possible. And also there will be some of the Higgs interactions, and either give some masses of the specific particle of the gauge boson, charge lepton or Kirk thing. And that is coming from the some mechanics of Gaussian values of the Higgs. And such a Higgs mechanism, there are two widgets. One is a particle that has mass, and the second one is Higgs interactions with such a particle. And based on such the Feynman diagrams, which is coming from the interacting Lagrangians, so we can calculate some amplitude, which is a probability amplitude from the initial state to the final state. That is called the Feynman law. That is a very simple example of the Feynman diagrams in the particle physics, electrons and electron scattering. And the electrons that have the charges, the electric charge, so there will be some of the mediating photons and the propagators is possible in the this channel. And we can calculate through the probability amplitude corresponding of this Feynman diagrams with the Feynman law. For example, the external lines of the electrons of the red lines, it contributes to the some the spinors that are U1s on the vertex, which is the meeting point of the two electrons and the one proton vertex. It contributes i.e. gamma mu's, which is coupling constants, and some Bartok structures, such contributions is the added multiplies and polarized the amplitudes, and such a photon internalized contributes to the polarized amplitudes as a propagated forms. And if we multiplications of all the contributions by this such a binomial, we can calculate the probability amplitudes. So there are some of the four external lines, 1 and 2 and 3 and 4. So we can calculate sort of the such as spinors and the two vertex and the one propagated represented here. And if we scale sort of this probability amplitude, we can obtain some observable quantities during the experiment, like the decay light and the spectrums as a function of the analysis of the angle. That's examples of the decay of the neutrons, which happens in the beta decays. And if we calculate sort of the probability amplitude of the corresponding the Feynman diagram for the neutrons decays and the integrations and using the Bernoulli's gold rule, then we can obtain sort of some spectrums as a function sort of the electrons, and that is equal to beta spectrums, and that is observable quantity in the realistic experiments. And that was a very recent result of the discovery of the Higgs. With the similar process, we can do sort of some Higgs production and the Higgs decays that the diagram forms, and if we can calculate sort of the some probability amplitudes using the Feynman diagrams and the observable quantities as some count light as the functions of the energy, and there will be some of the resonance signal, some of the bumps in the count lines, some spectrums, and that is some of the evidence of the Higgs existence. But there are still some of the various problem in the standard model. So should we solve such a problem with the so-called beyond the standard model Pearson? First of all, neutrinos that has a mass as the observations of the neutrinos oscillations, and the problem is the standard model didn't provide the neutrino mass. There was no right-handed neutrinos, such equal interactions with the neutrinos cannot be constructed, and very small masses that is very unnatural. So such as some of the new mechanism for the neutrino mass is necessary. And in the observable universe, there will be some non-baryonic materials like the dark matter and dark energy should be exist, but we don't know that the candidates of the we don't know that what is the exact list of the dark matter and dark energy. There are some several candidates of the dark matter and dark energy, like as axioms and the wind picked up photon ultralight dark matter, so we can tell such thing, but we don't know exactly what is the real dark matter and dark energy. Now, there was some of the naturalness problem, which is some very large hierarchies between the Higgs electroweak scale and the Planck scale. There are some of the loop corrections by the quantum field theory, and it gives some very large large correction for the scalar boson mass, and it should be there are some of the very unnatural sort of fine tuning is necessary. But if we assume that there are some supersymmetry particles and such additional loops by the super partner particles, that might be the offsets of the such loop corrections. And the binary problems standard model is it does not include some of the gravities of general relativity theory. There are some non-normalized by the power counting of the coupling constants Z, and such as Einstein reversal actions of the general relativity theories are not included in the standard model, and also there is no observable evidence of the spin graviton. So that is some of the overviews of the theoretical particle physics from starting from the introducing of the various elementary particles and their interactions, and the standard model Lagrangians and the Feynman diagrams, and some of the observable quantities, and some problems of the current theoretical particle physics, so-called beyond standard model.